Hello everyone, welcome back. So we have understood various device-related aspects of MOSFETs. So I wanted to give a quick overview of how these are fabricated, just so that you have an idea. Okay. So the fabrication of MOSFETs is a very complicated business, and to understand it fully, you require a full pre-credit course, which will go into great depth. But our objective in this course is not to do that, but we will just give you just an insight into, just a peek into how it is done. Okay. So we have seen that we have this, NMOS devices and PMOS devices, and we want to fabricate them on a chip. And we have previously talked about what a nanofab is, and we have seen some videos on that, right? I asked you to see some videos. So the way it is done is you want both NMOS and PMOS devices on the same chip. So there are a couple of ways of doing that. Okay. For example, you could start with an N-type substrate, N-type wafer. And then when you have an N-type wafer, you can quickly, have P-type diffusions regions. Okay. So when you have source and drain P-type regions, you can make a PMOS device very efficiently. Okay. But then how do you make an NMOS device on an N-type substrate, right? To do that, it turns out that we have to create a separate region, which we call as a well region, okay? Wherein, let's say your substrate doping is 10 power 15. And if I create a well of, let's say, 10 power 16 doping of acceptors in this case, right? Then we'll have a P-type well. Okay. So that is what is schematically shown here. So we are taking a substrate which is N-type, okay? And then once I have that, I can quickly make source drain diffusions of P, and then I can make this is a PMOS device. This is fairly simple, straightforward. But to make an N-type device, we have to create what is known as a P well. Because this was, let's say, 10 power 15, then I have my P well doping has to be at least 10 power, greater than 10 power 15. It could be maybe 10 power 16. Okay, greater than 10 power 15. If I have that doping, then I'll essentially compensate the donors, and then I'll create more acceptors. So you saw that there is a compensatory doping, and you get the substrate behaves like a P-type substrate. And then you have these well regions, which are source drain regions for your NMOS device. So you can fabricate this way. Okay. So you can have different regions on a wafer, which we can fabricate these devices. But then, one important characteristic is that we don't want these devices to talk to each other, right? Because this is ultimately a conducting substrate, right? There's going to be a lot of crosstalk. So to prevent that, you have to isolate devices from one another. So that we do by what is known as, in the 70s to about late 90s, I think we were using what is called as field oxide. Okay, this is no longer used because there are some problems with it. Okay, nowadays we use what is called as shallow trench isolation. But that's that anyway will be discussed in a VLSI technology course. But right now this is a field oxide, which is essentially used. It's a thick oxide. We saw gate oxide, which is a very high quality thin oxide. But then you can also have a thick oxide, which we call as field oxide. Okay, that is essentially isolating. You're creating barriers between different MOSFET devices. Okay. By the way, this is only one in the one axis, right? We are showing a cross section. But in principle, this field oxide will be surrounding the MOSFET on all directions. Okay, it's like a ring you're forming around a MOSFET to isolate it from other MOSFETs. Okay, so that field oxide will be created, and you can then connect these devices to form various configurations. This is one approach. But if you do this, you don't really have much control in the threshold voltage of the PMOS device, because whatever is the substrate, you're going to have that. Whereas for an NMOS device, I'm implanting my P well. I can control how much doping I'm introducing into that. So I can design my NMOS device better with this. Okay. You could also take the other approach wherein I start with a PMOS device, P-type substrate. So I can have an NMOS like this. Okay. Like N plus regions I can create. And then I'll create my PMOS device in a P well. N well. I keep mispronouncing it. So whenever you have a PMOS device, you have to have an N well, right? So we create an N well. Okay. And so you can have PMOS and NMOS devices on the same chip. But now if you do this, you have better control on the VT. Well creates, this well implies better control on VT. you're not dependent on the substrate doping, but you can tune. You can increase in some locations, increase the doping density of the well, and then increase your VT. That's possible to do. Okay. So eventually now in the recent technologies, what we do is we have both N well and P well. So that we call as a twin well process. Okay. So we take substrate, any substrate, it doesn't really matter, P or N, and then create a N well for the PMOS device and a P well for a NMOS device. Okay. And then you make this connection. So this is a twin well process, which is routinely used. So here we are only showing two transistors, but I can repeat it billions of times to create billions of transistors on the same chip. Okay. So that is how this entire process is known as planar technology, or I'll call it planar CMOS technology. Okay. This is the most dominant form, which was up to about 2011 or so, just 9 years, 10 years back. Okay. Till then, we were using this. Even in the most sophisticated chips, this is what was used. Okay. But then in the last 10 years, something has changed, and we will talk about it towards the end of the next week. Okay. All right. So this is CMOS technology, and this has been the workhorse of semiconductors for about 40 years easily. Okay. Starting from 80s when it became dominant to about 2010, I would say. So 3 decades. Yeah, it's definitely 3 decades. Okay. So well, you have this. So what? How does it help us? Well, I just want to give you a glimpse of what can be done. Okay. This is the simplest form of a CMOS device that you can think of. Okay. Wherein I'll connect an NMOS device and a PMOS device. Okay. By the way, this is a different representation for a MOS. Okay. This is basically meaning that this is PMOS and this is NMOS. Okay. So the circuit symbol for MOSFET, I've taken this from the textbook and it uses a different symbol. It's still the same thing. The physics is all same. Okay. It's I think less neat, so I don't like this symbol. I like the symbol that I've shown. Okay. So anyway, so what we are doing here is you're connecting both gates. Both gate of NMOS and PMOS devices are connected together. We call it input, and then the drain of both devices connected. It's called as output. The source of NMOS device, I'm connecting it to ground. The source of PMOS device, I'm connecting it to VDD. Just two transistors which are connected. And physically, if you look at it, it will be something like this. You have the P well, which is having the NMOS device, and N-type substrate, so you have a PMOS device here. So the drains are connected like this, and then the source is grounded. This is VDD. And how this is exactly done, how these connections are made, well, it is something similar to what you see on a PCB. When you see a PCB, you see this component and there are these copper lines which are running, right? So those are all metal connections that we are making. Something similar happens. Once you make the basic device, you do what is known as metal layers on the top, okay, of the wafer. And then this can be many metal layers, and then a lot of connections are made. Imagine, if you even ever try to design a PCB with, let's say, 100 components, you would understand how difficult it is to do the layout. Okay, but now we are talking about layouts connecting, let's say, billions of transistors. So you're going to have a lot of complications. So there's a lot of planning that is involved in actually how to do the layout and all that. Okay, but anyway, it can be done. Okay, so what? Once you have this inverter, what happens? So inverter, right, is basically a logic gate wherein I have my input and output, let's say. When my input is 0, my output should be 1. When my input is 1, output should be 0. How does this happen? Well, let's consider what is my, voltage physically. What is 1 mean? Logic 1 means VDD, supply voltage. Logic 0 means 0 volts. This is electrical equivalent. We are just using that, we are referring it as 1 and 0. That's a Boolean representation of the voltages, right? Physically, it has to be the voltage. So let's say I apply a 1. That means I apply VDD here. If I apply VDD to the input, what happens to this guy? When this is VDD, VGS is definitely greater than VT, right? So now, in this case, VGS is greater than VT. So NMOS is on, okay? So basically, this is on. I'll put it, okay, I'll write it here. NMOS, PMOS, okay? So when my V input is, let's say VDD input I have. So NMOS device is going to be on, right? Because VGS is greater than VT. What is the VGS of PMOS device? 0. And it needs to be negative VT, right? Negative of VT of a PMOS device is minus something, minus 0.5, let's say. So it has to be smaller than that. It has to be -1 or something. When VGS is -1, then the PMOS device will conduct. So this will be off. So what does it imply? This implies that output is connected to ground, right? So because this is on, output will be connected to ground. Now what happens when your input is 0? When your input is 0, what is VGS of NMOS device? VGS of NMOS device is 0. It is less than VT. So in this case, my NMOS device is going to be off, whereas PMOS device input is 0, so VGS is minus VDD, which is less than minus VT of the PMOS, right? Negative sense. So PMOS device is on. This implies output is connected to VDD. So output connected to VDD means output is 1. Output connected to ground means output is 0. So that's how you get this logic 0 and 1, 1, 0. This is the simplest CMOS circuit that you can think of. Okay. And the beauty of this circuit is at any point of time, except during the switching, right? If I'm at 0 or at 1, there is no direct connection from the VDD to the ground. So current cannot flow. And we already saw that this is, input is actually having very high input resistance. There's no current due to this. And this path also, only one of the transistor is on at any point of time, not both. If both are on, it's going to continuously dissipate power. If one of them is off, right? Let's say this is only having 100 picoamps of current. This, even if it's 1 milliamp of current, I don't care. Once the output discharges, you don't have any current flowing to this as well. So the overall current will be very, very small amount. And so we have very, very power efficient circuits. And that is the reason why CMOS has become the most dominant technology. Because in static case, that is when, let's say inputs are zeros or ones, not during switching. Switching, there's going to be some power dissipation, but only when it's 0 or 1 at that static phase, there's no power, very, very negligible power dissipation. It is not like that in BJTs. If you have a BJT, you try to make an inverter, you could make an inverter like circuit, but then it will continuously flow current. And because of that, the power dissipation will be so much that if let's say you made a transistor out of a BJT, I don't think it'll last, even 5 minutes or so. I don't know. I mean, it depends on the battery, of course, but it's not at all a very efficient device. It will just heat up like crazy. Okay. So that's why, CMOS is very, very popular. And so this was just a quick overview of what CMOS can do. Okay. We can design, what is a CMOS logic, NAND gate, NOR gates, and so on. That's again, a lot of, it's another course on CMOS design that can also be taken. Okay. Wherein you understand how to make NAND gates, NOR gates, what are the trade-offs, how do you choose the width to length ratio of these structures, how do you design them, right? All that is an additional course on CMOS VLSI design from the transistor perspective. Okay. So of course we will not cover that in this course, but that is something that you will learn at a later stage. All right. So thank you so much for your attention, and I'll stop here. I'll see you next week. Have a great day. Bye.